Good afternoon, everyone. I'm Shashank, and I'm here to present the paper on video action transformer network, which was done by Rohit Giridhar and his colleagues at DeepMind. This is the outline of my presentation. First, I'll be talking about the objective, then the proposed approach, the implementation details and the training part, the experimental results in which we will see the qualitative as well as the quantitative results, followed by the conclusion. So the main objective of this paper is to detect all the persons and classify their actions at a given point of time. So it is also very important to extract contextual information for the task of human action recognition without manual supervision, which is their objective. And they also wanted to build a model which is capable of representing all this information using self-attention without the use of recurrent neural networks, which we know are capable of capturing very good temporal information. This is the entire pipeline of their proposed approach, and I will be explaining. I will first go through the flow of this network, and then I will be explaining each and every block in detail. The pipeline is first divided into two regions. The first region is called the trunk region. So in the trunk region, they pass in an input clip, which is a series of frames extracted from a video. After this, it is passed through an I3D network. An I3D network is basically a 3D convolution network which is capable of capturing both spatial and temporal information. They extract features from this I3D network, which is represented here by this blue cube. They clip the center region and they claim it as their query feature, which they pass it through a region proposal network. These are the different regions extracted by the region proposal network, which are then passed into the ROI pooling layer. So from the ROI pooling layer, the features are passed on to the two-head, three-layer transformer network. So why is it called a two-head? Because they have two different transformers and three different layers which basically capture the contextual information as well as on the center object in order to classify a particular action. And after that, the output of this three-layer two-head transformer network is a blue cube representing the class of the action, and the bounding box, a tight bounding box representing localizing the actor basically. So now comes the action network. So the initial part was the trunk region, and now we describe what the transformer network actually is. So now we have the blue cube which has been extracted from the I3D, which was extracted from the I3D network. So they clip the center feature and then they pass it through a ROI pooling layer followed by a query preprocessor. A query preprocessor is basically used to downsample a 25x25 feature vector into a 7x7, after which is converted into a 1x1x 128 feature dimension here using two different methods. One is called a high resolution query preprocessor, and the second one is known as a low resolution query preprocessor, which we'll see in some time. The blue cube here represents the contextual information which they call it, and now it is linearly projected into two different features. One is called the key feature and one is called the value feature, which is used to compute the attention basically. So the query feature here is multiplied with the key feature here to compute the softmax attention, which is then multiplied with the value feature here to get the weighted sum. A dropout is applied on the resultant feature, which is then added back with the original query here. This added feature is then normalized. Then it is passed through a full feed-forward network, which is a two-layer MLP, multi-layer perceptron, on which a dropout is applied and then added back again here. after which a normalization is reapplied onto the added feature from this path as well as from the input here, and to compute the final the feature, which contains a tight bounding box as well as the class. And this is basically done in two different heads and in 3 different layers to get a final output, which is a very tight bounding box on the center actor and the type of action that the center actor performs. So now I will describe the implementation details. So the input dimension, so given a video sequence, they extract 64 clips, which is like a 64 frames, and each frame has a resolution of 400 by 400, so which represents the width and height, and 64 represents the temporal resolution or the number of frames. So since there are different classes in the data set which have very less number of samples as compared to the others, so they perform data augmentation like flipping and cropping to avoid overfitting. So once they extract the clips and perform the data augmentation, they pass it through an I3D network which is pre-trained on the kinetics dataset. So, and they extract the features from the mixed 4F layer, which is like the fourth stage of the I3D network. So the output feature dimension of the I3D network, which they extract from the mixed 4F layer, is 16 cross 25 cross 25. Here we see that the temporal resolution has been downgraded by 4, and the spatial resolution is downgraded by 16, which is like from 400 they came to 25 and 25. They take the center clipped image, center feature vector from this blue cube, as they call it, as their query feature, which is initially a 25 cross 25 feature vector, but after they pass it through a region proposal network, it becomes a 7 cross 7, which is the output of the ROI pooling layer. So basically the query here is passed through an ROI pooling layer, and we'll now see what the region proposal network does. So the region proposal network was first proposed by Ren et al. At NIPS 2015, in which, given an input image, they extract features from the convolution layer, from which the region proposal network basically proposes different regions where basically gives a localization regions from based on the input image. And then so these input regions may be of different resolutions. So in order to bring it into a common spatial resolution, an ROI pooling layer is done here, and then these so the ROI pooling layer basically brings all these different proposed regions into one common resolution of 7 cross 7, and that is why we have earlier seen that from 25 cross 25 the query feature becomes a 7 cross 7. So now once we get the output, once the output of the ROI pooling layer is achieved, which is a 7 cross 7 of the query feature, a query preprocessing is done. So this query preprocessor is basically a linear transformation of the original 7 cross 7 feature vector, which is obtained from the ROI pooling layer, in order to get a 1 cross 1 cross 128 dimension vector here. So after this, so initially the contextual feature, which is obtained from the I3D, is linearly projected into 2 different features, which is called key and value, which has been inspired from the transformer network, which we will see now. So basically the input feature, there is an input embedding which is done on the feature. So the embedding gives the X, so embedding acts as an extra information here. So this is the transformer network which was proposed by Vaswani et al. At NIPS 2017. So once we obtain this like feature vector, a linear projection is done using a fully connected layer. So initially, let us assume that we have a dimension of 16 cross 25 cross 25 cross D1, where D1 is the number of channels on this contextual feature. So D1 here in the original paper is 8, where they have stacked up these contextual features 8 times, and which is a hyperparameter and can be changed accordingly. So the FC layer is used for a linear projection which gives two different feature vectors, which is called key and value, of 128 dimensions. And each of this FC layer is learned independently for key and value, and it is not a common one. So once we obtain a key and value, we pass it through a multi-head attention. Here we can see that the input is 3. There are 3 inputs. So two of them are key and value, and the other one is a query input to calculate the attention feature. So how is the attention features are basically is calculated like this. So now we have the query vector which is a 1 cross 1 cross 128, and a key vector feature block which is 16 cross 25 cross 25 cross 128. So we do a multiplication, a dot product, basically a matrix multiplication, which results in a 16 cross 25 cross 1 vector. We normalize it using the square root of d, where d is the number of dimension, which is 128 here. We compute the softmax of this value in order to get the weights of it, in order to calculate the attention basically, and then this is multiplied with the value feature vector here, which results in A of R, which is like our attention features. So after which a dropout is applied on this and is added back to the original input feature vector query feature, which is a 1 cross 1 cross 128, in order to and then a normalization is done on this in order to obtain Q of R prime here. So we can see that the layer norm is Q of R prime is a layer normalization of Q of R, which is the output of the dropout. Q of R is the query feature vector, and the dropout of A of R, that is a dropout is done after the attention feature is obtained. After Q of R prime is obtained, we pass it through a feed forward network, which is a two-layer multi-layer perceptron, or a two fully connected layer, and then a dropout is again done on it to obtain Q of R double prime. Which is like this blue vector here represents Q of R double prime, and this process is done using a 2-head 3-layer transformer network to obtain a tighter bounding box and to categorize, which results in a tighter bounding box and the class of the action. So now I will describe the data set that has been used in this work. So here the authors have used the AVA data set, which consists of 211,000 training examples, 57,000 validation examples, and 117,000 testing examples. So the videos have been captured at 1 frame per second from 30 15-minute video clips, and here the center frame in the clip is labeled with the bounding box and all the different persons available in that particular frame. The evaluation metric which has been used is the frame level mean average precision with an intersection over union of 0.5 as the threshold, and the authors claim that unless specified anywhere in their results, they have stuck to mean average precision, frame level mean average precision. So in the first, so the authors performed different experiments in order to validate the performance of the proposed approach. So in the first case, they see how well the action classification is done given the ground truth boxes, meaning that they assume that the ground truth boxes, the actors have been localized with the ground truth boxes, and now they want the transformer network to predict what kind of class action it is, and using the proposed approach. So here they use their trunk region as I3D overall, and they used I3D versus a transformer network with two different variations in the query preprocessor, as we have discussed earlier, which is the high resolution version and the low resolution version. And here they say that the performance of the I3D with the transformer head performs well as compared to other approaches when the ground truth boxes are given. So now here they visualize the performance of the localization of the proposed approach. It means how well is the bounding box, the predicted bounding box as compared to the original ground truth ones. And here they say that if their proposed approach performs poorly as compared to the region proposal network, and this is one of the major drawbacks of this paper. Now here they analyze the performance of both the localization as well as the action classification part, where the transformer is used and the I3D network is used as the head with a high resolution query preprocessor. So from the region proposal network, the maximum regions that they extract are 300, and this is what they use throughout their entire work. And they obtain a 24.9 mean average precision, which is high as we see in later, which is compared to the state of the art ones. So here is the comparison with the state of the art approaches. As we can see here from that, we can see here that the proposed transformer network with the I3D as the head performs way better as compared to the other approaches in literature. And here 96F is the 96 frames that they extract as compared to the 64, which we had seen in the implementation details, and they obtain 24.93 as their highest mean average precision on the test set. So here we see the variations in the number of examples per class. As you can see here that for some of the classes the number of samples are quite less, and here the number of samples per class are very high in orders of like 10,000 videos per sample, and that is why the data augmentation is very necessary, such as random flipping, cropping, which is in order to accommodate for in order to avoid overfitting for these kind of high number of data per class. So here here is the analysis of the percentage of image covered by the box, where they say that the larger number of people in the frame, so the more is the performance of their proposed approach basically. And here it represents that the number of boxes in a clip with respect to the mean average precision value here, and here represents the number of clips per class in the total video set. So now we'll look into some qualitative results. Here we see here is the attention visualization of the two transformers. So basically we had earlier seen that there are two heads and three layers. So here is the visualization from the two heads. Here they also claim that the network is able to semantically capture the actor with green colors in the first transformer head, and in dark colors in the second transformer head, and which is like really able to semantically localize, capture the persons in the frame. And here is the attention map of the video clips, that the frames of the input video clips, and the red here represents high attention. As we can see here that most of the attention are on the actors rather than on the background, and it also becomes very important to understand the contextual information in order to categorize a particular action, and that is how the authors have been able to use transformers for their work. So here are some of the correct predictions. As we can see here that the action here is holding or carry, and here is fighting, where the localization has been like very good here, as well as watch. So in watch it is important to understand the contextual information also when we try to categorize this particular action. Here are some incorrect predictions. So here this is for the class of smoking. Here the person is thinking and so it is being able to categorize as smoking. Here this actor has been localized rather than this actor here. Here the mirror image the image in the mirror has been localized as smoking rather than this particular image here. And here both these actors are smoking, and still only one has been able to has been localized, which is an incorrect prediction. So in order to conclude, the action transformer network is capable to extract both spatial and temporal information along with the context for human actions and objects in the clip. And this network is the embeddings and the attention map here have semantic meanings, as we had seen in the qualitative results, where each transformer head was able to semantically capture the actor in different colors. And even though the authors claim that they don't use optical flow information or motion information, like using these kind of motion, explicitly using motion information would boost the performance of their proposed approach even further, but they do it with just using RGB information. Thank you. That's it.